After some technical difficulties here, but I can hear you guys. I can see your screen.
Oh, good.
Good.
So we should introduce ourselves. I think Neil's a good. He can give the overview of what we're doing. So.
Oh, I can I? Okay.
Yeah. If you like.
Sure.
I can do it.
Welcome to the April 1st edition of The Electric View. I'm Neil Thompson. Today we will have a special guest, Gary Doskas, in addition to Mike Evans, David, Buddy, and Heather. We are going to explore Gary and Mike's work with this subject and see how it may pertain to the world we live in. We're basically doing Happy Easter, yes.
Yeah, thanks for joining us on the holiday like this.
Yeah, no problem.
But we do a podcast twice a week, and this one is you're the guest of honor this week. So, well, I'm glad that you could make it as well. It's good to have you here. I'm mostly we deal with the electric universe model as opposed to the conventional model. That seems to be, but it touches on so many things, and obviously the subject of sacred geometry has come up. Buddy's a big fan. Heather is an author and writer, and she also brings a much more holistic point of view to certain things with regards to astrology and other things like crystals that I would have no idea how to identify. But like I said, I love talking about geology, but I'm an electrical engineer. So, and Dave is the guy, the madman who decided to put all this together. So.
Somehow it gelled into what it is. So we're kind of exploring what it is. So.
We'll have more people coming on, I assume, because Robert said he'll be joining us, and I'm trying to get a hold of Tim as well.
So basically, it's a free flowing conversation, and we have on different guests, and we all. Ask different people on our contacts and our networks to come on, and we debate and talk about different things, a lot of the time surrounding electromagnetism and light and sound and really investigating reality, Birkeland currents, electricity, and whatnot. So, I received your contact. Someone posted it on my wall, one of your videos, Gary, and I looked at it immediately. I sent it to Terrence Howard. I don't know if you know who Terrence Howard is, the actor.
No.
But I was just right away. I was just like, yes, Terrence needs to see this, because we are all very in depth studying light and, like I said, the electromagnetic spectrum. But yeah, when we saw your work, we were very ecstatic and curious to know some more. So yeah, thanks for joining us on the Easter show here. And if you wanted to maybe give us a little bit of overview about some of your background history and how you got to get into spherical harmonics and stuff.
Yeah, I guess I'm an electrical engineer by trade, so that was my day job. In the high-tech industry, working for Advanced Micro Devices, or AMD.
Okay.
I recently retired. It was a bit of a draw on my time to have a real job, and then something that I really liked doing and wasn't getting paid for. And so back in 2011, I just got sort of a revelation of sacred geometry that kind of drew me into it. And I'm a hands-on person, so I like drawing with my hands and experimenting things right in front of me. And I just came across some of these relationships between circles on a surface of a sphere, and it just drew me in, and we're just kind of compelled to write about it. So that I've actually since then I've I've retired this last year, so I got more.
Congratulations, by the way.
Yeah.
Yeah. We were with the same boat here.
Yeah. So right now, I guess I've really spawned off to be a bit of an artist or an aspiring artist. No one gets to see my work, but I enjoy making things, and most things I make now relate back to spherical geometry to some extent, and I either make them out of wood or plastic or metal. Now I have a 3D printer, so I make various other kind of geometric models that are construction kits, puzzles, and mostly to deal with magnets and magnetism. I've made a few different motors that I've experimented with. So I'm kind of all over the map, but everything I do now has been inspired by the work I did back in 2011, 2012. And it's still, it's a big part of who I am today. So it's good to see someone show some interest in something that I did way back when. Yeah, and this was what you're showing there is just a very simple relationship between a circle and a sphere. And, with a little bit of, simultaneous equations and solving for it, it started to, it actually could describe what I was doing experimentally. I just would take a wooden sphere and start drawing on it like I would on a flat piece of paper. And I guess we've all seen the flower of life pattern that you would see on a flat surface. That behaved very differently on the surface of a sphere, and you get I call this a fifth harmonic. Once you get the right size of your radius, you're actually drawing cones. Like your compass point is, say, on the North Pole, and you're drawing these, on the surface. And it was just kind of a natural. Once you get your compass at the right, radius, this pattern just emerges. Just naturally, just by drawing one circle and then just moving your point to the circumference of that circle, and they just naturally intersect. I just felt the harmonic that this kind of represented, and then I just I started experimenting with larger radiuses to see, well, it must be a fourth harmonic and beyond.
What is the relationship off equator? Like, it looks like it's about plus 30 degrees up and down, maybe, or maybe 20 degrees.
Yeah. This is about, I guess, the radius here is like 1.05. So the radius that I'm talking about would be the from the North Pole down to that. Yeah, I'm trying to think about how that would relate to a degree on the map.
I was trying to wonder that myself. I'm looking at let's see, the circular radius, because none of them are right over top of the equator.
Right. Yeah. They're not great circles. They're lesser circles.
Right. I was trying to wonder what the radius difference was. Like, trying to just in my head trying to figure out, because there is one that will perfectly match.
Yeah. Okay. I could easily. I could calculate that and send you on that. Yeah. We can have
it's an icosahedron, right?
Yeah. So it is exactly. It defines all the properties of a icosahedron. And then, like, the fourth
one, you can see the dodecahedron in there too.
Yes, exactly.
That ball shape in there too.
Yeah.
Ball shape.
Now, if you extend the radius to basically the square root of 2, you get down to the equator, and that would correspond to what I would call the fourth harmonic. Because now you're actually defining an octahedron as well as the cube.
It's so odd that you mentioned root 2. Buddy works on root 2.
Yeah, everything.
I'm working now with quantum modules. I'm not sure if you know what Buckmeister Fuller had done in synergetics, where they have
vector equilibrium and
and he defines something like a mod A and a mod B, two very basic irregular tetrahedrons that you can build up most of the shapes we know today. And I find out the square root of 2 and the square root of 3 combine and do a lot of interesting things together as well.
Mm-hmm. Do you find relationship between pi and phi? I mean, I know you talked about it a little bit.
Yeah. Well, I in this case, actually, the icosahedron has that relationship to phi.
Mm-hmm. Yeah, you see the gold rectangles just in there for sure. That's pretty amazing, pretty fundamental, and there's a lot of beauty in it.
And then, when I got to the fourth harmonic, I was just doing kind of experimentally, and then I went back and I wanted to come up with a formula, which with the general solution that you showed earlier. And once I was able to sort of feel comfortable, it did represent what I was doing. I was able to predict where the third harmonic would be, and I just, I found I got a value for it, and actually, if you show this for the third harmonic,
I gotta find where it is here,
but it was difficult to get to because I needed a compass that would go into the southern hemisphere, which was a little challenging to do, and here. So you can see, so the compass would have to, dig down into the southern hemisphere to create a circle, and then it would just naturally, as you do the same sort of flower of life pattern,
right?
You would divide that circle into 3 parts and create 3 other circles that would define essentially the tetrahedron.
Mm-hmm. Mm-hmm.
And you would think you would just, since the circle is actually a lesser circle, you could have done it from the South Pole, but you wouldn't get the same result. It wouldn't converge into a pattern.
So what tool did you? Is it a different method of getting it? What was that?
Well, yeah, I made a compass that would look a little bit like this shown here, like kind of curved around.
Oh, like this one here. Right?
Yeah.
Uh-huh. I got it.
And then, once I had the general solution that, like I can predict something, I didn't know what it would look like unless I drew it, right? So even though I knew that radius I call RTA, that, like the edge of the cone, I didn't know what it would create until I went and drew the first circle, and then, tried to draw a pattern to see if the pattern would converge, and it would converge after 4 circles, into defining the tetrahedron. And then I thought, well, are there harmonics in between the third and fourth and fifth? Right? I call them fractional harmonics, and that's my amazement that there's an infinite number of fractional harmonics that would say be halfway between, or any way between the second and third harmonic. And if I just, if I put that value to say 3.5, which if you use an improper fraction of, say 7 over 2, it would give me out a radius to set my compass to. And then I only realized later that the numerator and denominator, like say 7 over 2, described that, well, it's going to divide that circle into 7 segments in 2 revolutions around the circle.
Right.
Wow. Nice.
And, and there's another one for, say, 7 over 3, like it's a K-star polygon, I think they call them generically.
Okay.
Right? 7-pointed star, but actually it's a skip of 3. Like the points are drawn every third point instead of every second point. And if I put in, the improper fraction 7 over 3, I'll get exactly that. I'll get a 7-pointed,
Right.
heptagon, and that will continue through all the various harmonics that I didn't show it in this video, so I probably hadn't come across it yet. That's where my biggest interest that I haven't gone back and really pursued much is all the fractional harmonics that exist in between, generic harmonics.
Right. And then you can see it once you've drawn it all out. You can see the relationship, obviously, right? Then.
Yeah.
Just immediately, right? Very cool.
Can we look back up at that one that you had up originally, the circle with the 3 rectangles in the center of it?
Yeah. Okay.
That was the fifth harmonic.
Yeah, that's right. Yeah.
Okay.
This here?
Yeah. I just I mean, if you guys see it, but if this was the Earth globe, right? Each of these points, these intersecting points, actually lands on a very volatile area on the Earth. Like if you put that center point right there on the tip of that pink one at, say, the Yucatan Peninsula, then you would get points like Iceland would be above it, and then Alaska would be on the other side. And then when you come down, the one in the bottom would be like close to Vanuatu, and all through the one in the middle there would be kind of a little offset. But you know what I mean? Polynesia, which we're having what is
a lot of volcanic activity.
Yeah, like Papua New Guinea is like the worst place in the world to be right now. It has just been shaken for like a year now, nonstop. Is anybody else noticing that? Is that in this picture? Am I like an if?
Oh. Yeah. Go ahead. Yeah, there's something I could bring up that kind of ties into it, but just continue the explanation, Heather, because you're right on with it. I think.
I'm just thinking that. Yeah, thank you. Because if you look at it, you can kind of see. You could put like Japan there. You could put things right on those lines that are, like kind of like breaking points, right, where the Earth is kind of separating itself and like relieving pressure, like we were talking about earlier, pressure points, maybe these convergence lines.
It also, isn't that where the sunspots happen, along those star tetrahedron lateral lines or around the sun? Like the Earth? Like the hot spots? Is that what you're talking about?
Yeah, but I guess on the sun it isn't quite the same as the way that the Earth digests it, or the Earth expresses these things. I mean, I don't know either. I don't know the answer to that question. But they, like, sunspots tend to be a lot, like, closer. They look, from following them, they seem to be along, like, the equatorial lines, you know, which shift.
Well, except they don't cross equators. But
they don't cross equators.
I was thinking, what reminded me of this when I'm looking at it, I'm reminded of Michael Tellinger and his network of sacred sites around the world type of thing.
Yeah.
I don't know. Obviously, it takes me a little bit before I'm going to like just suddenly buy into something like that. But immediately, just looking at the drawings that Gary did and seeing the circle, I was beginning to see this is a point and this is another point, and then I was like, okay, they're just offset from each other, just like by 30 degrees, and then then he, as you said, over 7/2, and then started getting 7 points at every refraction, and I was every 2 rotations, and I was like, okay, well that's how you put pi in there, and start getting back to sine wave studies that I used to do in power engineering.
Have you done 8/5?
The fractions have to be between 2 and 6. So probably would be a.
Although 8/5 is a pretty good relationship between the kilometer and the mile.
And it's also how many, like the amount of vortices on the north and south pole of Jupiter.
Yeah, I did notice that.
Oh, yep.
Yeah, that's the grid thing that I was thinking about. Yeah, like I said, It just reminded me of that.
Yeah. We'll follow wherever the conversation leads, Gary. So you have to.
Yeah,
we're kind of flow of consciousness, as you can see here.
Well, I'm hoping to learn more than I contribute.
Oh no! It's what you're doing is right up our alley for sure. So it's really a pleasure to meet you. So.
Yes, and from Montreal too.
Yes, I am. Yeah. Oh, another Montrealer in the mix.
No, I'm from Moncton.
Okay, all right.
Where the Trailer Park Boys are from. No,
that would be.
No,
okay.
they're from.
Oh yeah, we can tell where. Let's see. So we've got Detroit, the Detroit contingency with Heather and Buddy, right? Michigan.
Yeah.
And I'm in California.
Okay. I'm actually living close to Boston. I've been in this, the U.S. for 20 plus years.
Okay, nice.
But born in Montreal.
Okay.
Lived in Ottawa for many years as well, before I came down here.
Sorry to hear that. I was actually born in Oshawa, so my whole family's from down this way, so.
So one of the things that I ran across, you talking about Planck's, just to get a little different angle on things. Yeah. Planck's constant, and you're looking down that rabbit hole a bit. I heard this description of Planck's constant as I was reading through some of the stuff, but it's if you imagine a grain of sand, and then you expand that to the entire visible universe, right? The size of Planck's constant is the next grain of sand within that universe. Yeah. That's an interesting, visual to me. So, but what's your impression and that exploration that you've done with that?
Well, I didn't think there was any limit to any dimensions. I think it actually went. What was interesting is I asked the same question. What the general solution would predict, what the sixth harmonic would be, right? And basically, what I'm asking is there a circle on a sphere that if I use the same radius that I drew the circle with to try to mark off segments on the circumference, could it divide it into 6 equal parts, right? Like the fifth harmonic, I could set a radius and it divided into 5, and the fourth. But if I backed up and said, well, what does the solution tell me if for the sixth harmonic, if it's going to compute a value? And it came back and basically said, well, if your radius is 0, it will divide the circle into 6 equal parts. It sort of came back with an answer. And so it basically told me that as you take curvature away, so as you make your radius smaller and smaller and smaller, you're getting flatter and flatter and flatter. So there's always some curvature, except at a point when you reach 0. But if you look at the general solution, if you plug in the value for the sixth harmonic, it would come back and say, yeah, it works, but it's 0. So so at some point, just before it's not 0, all this geometry still applies. And I just, I don't know much about Planck's constant, but it just sort of led me to.
Neither do we.
Yeah.
So yeah, but it's certainly a cornerstone piece for like the foundation of mainstream physics.
Yeah.
And which there's different perspectives in the group, but like I think Buddy and I are probably the most the strongest ones that question the foundations.
Yeah, and this book here was just something I wrote just after watching a show called "What Happened Before the Big Bang."
Do you suggest we watch it?
It made me think. It's done by BBC, so it's fairly well done. A lot of it was done in Waterloo, Ontario.
Ah.
In the Perimeter Institute, I think that's what it's called. So I wrote this book because I want to have something to show all these physicists who were at this convention on string theory. And I don't know anything about string theory, but I was really interested in the people that were talking on the video. And in that book, I proposed that at the very smallest level, these geometries that I show here have a growth rate, so that if the strings were actually just small circles, but interacting with each other, following certain geometric rules, it could explain a lot of different stages in, energy or whatever kind of state you'd want to. And in most of these pictures you see here, I have a sphere that's fixed in size, like that wooden sphere is fixed, and I'm changing the size of the circle and seeing how different size circles relate to each other. But if you actually keep the circle the same size and just start rearranging the circles, the virtual sphere that it sits on grows in size. Right? So it gives you a way to grow. Yeah, probably a few more slides down.
Okay. There we go. Let's see. Almost.
Yeah. Maybe just after that. Maybe. Might be just after that. Yeah, that's pretty close.
This?
Yeah. Actually, there might have been a slide just before that.
Okay.
You might see some increasing size.
Yeah. I saw it at one window here. Huh?
It's in that vicinity. That's kind of a...
I'll let it play.
Okay. And that's just a physical view of the internal sphere, kind of represented by that, the center of it. Kind of represents it's getting closer to it on.
Okay.
Or either you might have just missed it, or it's just after this. Yeah, probably just after this. Was probably just before that slide.
Okay.
Yeah, okay, it's just after this. Yeah, this is the. Yeah, so this is if the sphere is the same size, the circles I'm getting from smaller to smaller.
Right.
But I took the opposite approach. So I kept the circle the same size, and then I just like I rearranged the circles in the same way, and the sphere that they existed upon. Actually, so if you continue a few more seconds, I think the next slide down shows the other way of looking at this.
So, before the Big Bang got you thinking about this kind of stuff?
Yeah. That's hold it right there.
Okay. Yeah. The one right back.
Yeah. That's
Yep.
Okay. Yeah. Sorry, what was your question?
I guess it's rhetoric. I was just saying. So the documentary Before the Big Bang got you thinking about these fundamental shapes and stuff.
Yeah.
And harmony. Okay.
Yeah. And this was just another thought experiment that these are the same geometries, but the same notes. So the 4V represents like an octahedron, like the 6 vertices of an octahedron. And then as you expanded the circles, so each circle now, actually, the first figure, it looks like only 3 circles, but it's actually 6. Each circle is a pair. One's drawn from the North Pole, one's drawn from the South Pole, and they overlap.
Right. Got it.
But as each one of those pairs of circles separate, they start forming their different patterns. You see the one in the middle is that the two, that one vertical line is now one to the left, one to the right, starting to kind of create a cube to some extent.
Right.
And the circles are the same size, but the virtual sphere that would be sitting in has grown. And the very last one, the circles have separated just to the point where they're still touching. Right? So there's certain quantized points where I think these circles would have stable points.
Right.
So the most stable one would be the one on the left, where that's the tightest you can ever get packed. And that would you couldn't get any smaller than this. This is where structures would break down.
Right.
When you put in more energy, these strings or circles, whatever, would start separating to a point where they find the next stable point, and that's where the radius would be like 2 over root 3. And I just love seeing these numbers when I start doing
yeah.
Nice.
Amen.
Nice.
And it's always a cube, too, right? As you separate them out.
It's reoccurring. Yeah. In this case,
inside, it's always a cube.
Yeah. Now,
so it's that sphere cube relationship.
Yeah. Now, for each note, like for the fifth harmonic, it has many more growth steps. There's more circles involved.
If that's root root 2 on that sphere at the right side, if that's correct, that would mean that if we were just doing RMS power, I'm trying to think about if you cut off all root mean square, root 2.
Okay, cool. Just for the viewers.
0.707. But I was just wondering, because that means if you did it on a sphere, then there should be a point where the inside of the sphere will be equivalent to, if you cut along those lines, would be the area, the volume of that would be equivalent to the volume of the square that's left. I know that sounds strange, but I think I'm right.
Yeah. What's going on in your mind? How are you visualizing that?
Well, because it's a sine wave, you see, if you roll it out. And then if you want to know how much basically root mean square means, and you should know this anyway, it's area under the square, would mean how much actual DC power it takes to make that sine wave. That's all.
Right. Thank you. Thank you. That's the kind of stuff we need to know. That's awesome.
Yeah. Anyway, I was just wondering if it's root 2, that means if you cut it, I'm thinking it would be the same area of each one of those things would be the same size as that square. But that's just me thinking now, because I'm trying to put the root 2 in there, because there's a part of me that just has to, DC rectify that,
Gary, so someone tagged me. They're familiar with my content and some of the discoveries that I've come up with. Someone tagged you on my content and said that you need to see this because it reminds me of your stuff. And what I'm seeing here is direct relation to something that I've called Aurora Star. I just sent a couple of images you might have seen pop up. Okay. David, if you could please pull some of those up. These are the harmonics of spheres according to what I understand here. See how, and these are all conic, what you call the conics, right?
Yeah, yep.
So if you could zoom in a little bit, and you can see that if you were to place the compass at the top, north or south, these lines would be drawn on the sphere.
Yep.
Down here.
Yeah, either or. Yeah, perfect right there. See, you put the compass on the top and you draw any one of those lines. See how they move through the sphere? So you could envision it in this type of manner. See where these fault lines are? All of the lines at the top or at the bottom? Every single triangle in here is equilateral triangles as they move and propagate through a sphere. See that? That line on the right?
Yeah.
Now, can you relate that to some of your work? Because I see it there.
Yeah, I've got a gray blotch on my screen here. That's.
Oh, is it? Yeah. It's because of the contrast on the images. That's what I'm trying to break.
Oh no, the way I brought up Skype, I don't want to mess with anything.
Okay. Okay.
So I got this thing called share your screen, browse the web together, view documents together. and I don't know how to get rid of it. It's right in the middle of everything I'm viewing, so I can see around it.
Oh, okay. Okay, gotcha.
There's probably an X in the corner. I don't know where it goes.
Yeah. I don't feel like messing with it at this point because I'll probably lose you.
Oh, you're probably right.
It's probably just a drop-down menu or something, but right. Yeah.
Yeah, but it's all grayed out now. But it's fine. If you just scroll up a little bit, you can see a little bit better.
Yeah.
Yeah, so I see those triangles, saying that you're... what those represents?
From your spherical... See, what I am understanding is this is pretty much the same thing as what you're doing. If you were to put a compass on a sphere and draw that top line, any of those lines at the top would create these connexes that you're talking about. And you see how...
Kind of see on the side, I think, what's going on.
Yep. Right? On the side, there's motion. Motion's happening. And this is how waves move through the ether or whatever they're propagating through. But do you see any correlation with your work here in some of this?
Yeah, I'm starting to see it a little bit.
A lot of this stuff takes a little focus and meditation on
right.
it.
Right.
Yeah, but there is something common there.
Yeah.
It's just
very cool.
It's two different ways of representing the same thing to some extent.
Yes, that's what I thought. So that's why someone tagged me, because my work is a reflection and similar to yours. So I'm. If you want to go to another one of the images, David.
Yeah, let's see.
Please.
Okay. Let's see. That was that one.
Yeah, that's good. That might be kind of the same thing there. Yeah, it's kind of the same thing. And then if you go to the next one.
Okay.
Hold on. I love the Keplerian orbit thing.
I am definitely going to go. I have some wooden spheres at my house.
This one doesn't. That one doesn't.
Need some croquet balls.
Oh, it doesn't like that one?
Doesn't like that one. Yeah. Nope.
Nope.
Okay. That's fine.
On that. Yeah.
So,
nope.
If you could go back to the one that we were on to begin with. Yeah. Now, these lines? You're talking about these lines, individual lines, as harmonics. On the gradient of the top of the sphere here you're looking at, each one of those lines would be a harmonic, and some of them would be subharmonics that you're talking about. Correct?
It'd be interesting, if what that conical radius is, right? So, like the length from the North Pole to each one of those circles.
Yeah, it's always this ratio, those fundamental whole number ratios, right?
Yeah. That's it. There are some whole number ratios. The ones I found, actually, there's a second harmonic, which is a prism. For some reason, I don't know why. I just used the numbers right out of my general solution. It'll draw what would represent a prism. But there's a lot of fractional ones that I think might be represented in what you're referring to in that last picture we were looking at. It could be some significant harmonics, like some fractional harmonics.
Mm-hmm. How would I go about figuring out what fraction it is based off of, the compass gauge?
Yeah, if you could say, draw any one of those on a wooden ball like this, and see how many times it takes. So draw your first circle, and then move your compass point onto that new circle you just drew, and then start marking off segments, right, like you're doing. It's more likely it's going to be a fractional harmonic, so you're going to be going around the circle more than once.
Mm-hmm.
And you just have to find out, well, if I went around a circle 4 times and I divided it into 11 segments, well, then my fractional harmonic is 11/4 or something.
Ooh, okay. David, could you please go back to my image real quick?
Sure.
I have a couple more questions. So what would the star tetrahedron harmonic be? That first one of the star.
The white and red one that you first looked at?
This one right here.
Oh.
The angle, I'm sure you probably have already drawn it on a sphere. Maybe not, but
Yeah.
do you know what the harmonic of the triangle of the tetrahedron is? On a sphere, like that particular line?
Okay, could someone trace that with your mouse?
Yeah, I'm not sure, buddy.
Okay.
I mean, star tetrahedron. I mean, it's basically that tetrahedron angle that you're looking at, right?
Yes, the main star tetrahedron in the center, the main star tetrahedron, the fundamental. I don't know if that.
You're doing it. This is what you're talking about.
Yes.
Like that, and then this up.
Yeah.
Right. Yeah.
Yep.
Okay.
Yes,
It's on the it's on the outside of the sphere. Yeah.
Okay.
Oh, so this one here on the this one and this one. So the ones that are closest in toward the equator.
Yes.
Yeah.
Do you know about those, Gary, at all?
I'm not sure if I do.
That's a pretty famous one. It's a Merkaba. For some reason, it's come up in some of the stuff I've been doing. So.
Okay. Cool. I got some homework to do then. I'm going to buy some spears. You got me hyped, man, for sure.
Cool.
Now, in this case, where would a compass point be?
At the top, at the north.
Well, I think it's ultimately if you took like you already did it with where you inscribed the tetrahedron in the sphere. It's that was that the second? Did you say second homily?
That would be a third.
Third. Okay. Yeah. Right.
That answers my question.
Yeah.
Perfect.
So and then it's the the same from the opposite pole, right?
Right.
Yeah. Right. So you just flip it 180 degrees.
Yeah. So then I would just take each one of those increments and create spheres or create circles, conics is on the sphere, and then I would find out each fraction of those, right?
Yeah, you have to have really good measuring devices or good. There's going to be some little bit of error because the wooden sphere may not be perfectly spherical.
And then the point's going to go into the wood a little bit, which would change it.
Right, exactly. And I found this was so precise that I found that even like the lead point of my pencil as it started wearing down affected my measurements.
Oh yeah, because it's gonna wear on that angle too as you draw it around. Cool.
Yeah. But once you go beyond the fourth harmonic, one small move makes a big difference in the result. Like I said, it depends how deep your compass point goes into the wood. There's certain things that you just got to be aware of. But if you could actually start with something that you knew it should, I could give you a value for a radius for the third harmonic just to make sure it converges. You probably want to check that you got something that just you can prove that you're doing it right. So, but yeah, I can see some commonality there.
Cool, nice. Yeah, I'm excited for sure. So what types of ventures have you acquired from coming up with some of these discoveries, or where has it led you to some other cool areas or arenas?
Yeah, I'd say it's more. I spent a lot of my time making like geometric models. My very first model was actually making. I moved away from drawing lines on a sphere to actually taking metal rings and joining them together, where I thought they'd represent each one of these notes, and then trying to come up with an engineering solution so they could move in unison. They have to move and spin. And then I just took it, making cones. Right? So each one of these conics could also be basically a cone. And I continue to take various other ways of representing this geometry with physical. Yeah,
that right there. Yeah, that's it.
Yeah.
Yeah, so that's what I would do. Have you ever taken actual cones and set them on top of the spheres coming off so you can show the conics?
Yeah. You can do both.
Okay.
Yep. Now it's a little a little more challenging on the outside, but depending how you can actually join them together. But yeah.
What's one of the more perplexing? What were you calling them? Subdivisions, or what were they?
The fractionals?
Yeah, fractionals. That's the word. What's some of the more perplexing fractionals that are like mysterious? I love mysterious.
Well, the seventh, the two versions of the heptagon, or the seven-pointed star, really is intriguing. And actually, it led me to do some side research on just the heptagon itself.
It made me research into dragons.
Oh, yeah? Oh.
Game of Thrones, the 7-point star. Never mind. Just too much into that show. Anyway.
That really intrigued me. And then I started building electric motors. Well, actually, before that, I started making hoops that represented these notes. But I wanted the hoops to move, so I had to give it some ability to rotate with respect to each other. And I would take a series of, say, 4 hoops that would represent, it'd be the cube octahedron you can represent with 4 hoops. And I was actually just building them together, taking 4 hoops and physically trying to make it would represent the circle that the sphere was sitting on. And in the process of joining them with little nuts and bolts, the thing started falling and moving in ways I didn't anticipate. So, wow, this was kind of like a 4-dimensional gyroscope to some extent.
Mm-hmm. Sort of like what we're looking at?
Yeah. But it was, so each hoop was connected to both adjacent hoops. So but it's like a kind of a Russian doll. So now I had a hoop inside a hoop inside a hoop. But they had pivot points between them that would allow the hoops to rotate with respect to each other. So the first hoop was connected to the second was hooked up to the first and third, and so on. But the tricky part was, that's a good pattern there that I started looking like.
Uh-huh.
But the inner hoop, the only way to get the inner hoop to react with the larger hoop was with a magnetic pivot. So this was allowing the hoops to kind of spin through each other to a certain extent.
Mm-hmm.
Actually, on a future meeting, I could actually be better prepared and.
That'd be great. This is it's more meet and greet than anything, but we're just kind of getting started. But it's the content is just really resonant, to do some punishment there or pun making.
Yeah, and we also it's Easter, so we don't have as many people on as we normally do,
right.
And we would be definitely having debates on like seeing the patterns and noticing that they're there. I'm very much wanting to get down to the nitty gritty as to how are they there, what are they in relationship to, what do they represent, do we see these in nature, that type of thing.
Yeah.
And I'm a big fan of, obviously this is why we're all sort of like we're very much into Rupert Sheldrake's morphic resonance, which of course directly dovetails nicely into the electric universe models. So.
Yeah, everything that we're doing for sure. I would agree.
We have people who work on the micro scale, right down to quarks, and then we're into, I'm obviously sort of in the electric engineering middle part, but, I'm like, okay, well, imagine this is a charged sphere. Okay, what's going to happen when it's immersed in a sea of plasma? Okay, now what am I looking at? And now what type of forms will there be if there's a 7.83 resonance going across the surface of 50 kilometers between these 2 points around, what is this cavity? How does it work? That type of thing. So it's very, very, obviously there's something to it, or we wouldn't have these wonderful astrologers wouldn't care about planetary motions as nearly as much if there weren't some sort of all-encompassing doomsday fear about it.
Yeah, there's a lot of interesting stuff. Most of my analysis, actually, in the end, I realized I was just analyzing the surface of the sphere.
Yeah.
There's just so much that you can learn from that, and it's nothing I was taught in school.
Right. Yeah, I mean, there's so much of this stuff that was never touched on, and I was talking to someone the other day, and it's like, as I was a kid, it's like, oh, look at these platonic solids. I hope, I someday I get to them, And it's like, I went through all this mathematics and all engineering and stuff, and it's like, we never touched on it. It's like, And what about the golden ratio? I never touched on that. And what about, like, if you do harmonics, what about the notes in between the octaves? Why didn't I touch on that? You never did.
And of course, we also began to realize that the forms are happening.
Calling in. Hold on.
Well, answer it. Come on.
Oh, man.
That's you.
I can't see.
What do you mean?
I can't see that.
Oh.
Hello? Is this Michael Evans?
Yes, it is.
Holy cow.
All right.
Excellent.
Happy Easter to you.
Sorry I missed so much.
Oh, no problem.
We're just getting to know Gary here. He's new to the EU, but definitely into the resonance ideas, and he's showing us some of these relationships with spheres, and obviously the flower of life. And we were just started talking about platonic solids when you walked in.
Wow.
So
right up my alley.
there you go.
There you go. Right. So, and I'm kind of showing Gary what I'm doing in the background, by the way, is I'm playing around with some of the stuff that's somewhat, tangentially related to what you're talking about. So,
On Argos Vu. Yeah.
So,
Had to throw that out there.
So, by the way, now look at this opportunity. I can show off Mike's stuff. So let me come here. I gotta get my. Yeah, go ahead. Please talk amongst yourselves.
I wanted to emphasize some of the importance of why we're talking about spheres and the modality of our mind setting of before the Big Bang, fundamental shapes, fundamental units, and in general just bring importance to the sphere, because it's part of my theory is that time exists on the edge of spheres. But where are these spheres coming from? What are these spheres, And reality is, according to a lot of what we're studying, is reality is seeming to be composed of pressurized spherical units, a spherical coordinate system, So, you got into the idea of mapping out the sphere, and I guess, if you could go into more about your passion about spheres and some of your ideas about them.
Well, yeah, there's so much structure to it that and for some reason I met with a group of people, and we almost started a group called Field Structure, or Field Structure. I'm the kind of person that just likes to see something with my hands and kind of explore with it. So often, if I have an idea, I just start building it, and the more pieces I have, the more I learn. But I couldn't have learned just by writing on paper or trying to make an animation. You get your hands in it. It's not, every mistake you make, you can actually learn from it. So it's just type of enlightening to just go down the path and kind of see something that is kind of simple but new. I like this. These pictures here, one of the other models I made was that kind of looks like a void between spheres, right?
Yeah.
Yes, it is.
Right, exactly.
It's also the shape between 4 or 8 tetrahedrons.
Yeah, okay, yeah, I can see that.
4 bubbles.
This one here. See?
Yeah. I made a whole geometry set that just consists of voids.
Nice.
It's all the stuff that you don't see. What's that?
Do you have a site where we could see some of this? If you have it out, have you released it?
I do have a few things I've uploaded to YouTube, and I'm on my wife's computer right now, so I'm not really set up to.
Gary, I went to your site yesterday and looked at some of your things. I left a message there with images, the geometry of light. Have you had a chance to look at that?
Okay. Yeah, unfortunately, I don't really maintain that website, but I think that it's the.
Was your YouTube, I think, maybe.
Oh, YouTube channel? Okay. All right, I'll take a look.
Well, if you Google geometry of light, you'll see where I've broken down the sphere into its elemental form, which is comprised of approximately 180 tetrahedrons. Creates a sphere.
Okay.
Yeah, if we could pull up some of Michael's work, that would really dial in real well right now.
Yeah, because when I looked at your stuff, now you work with Nassim, is that correct? Somewhat. Not at all.
Yeah, I'm not sure.
Nassim,
The name rings a bell that someone may have actually contacted.
no problem.
Yeah.
Long-haired Hawaiian fella.
Yeah, right.
Can't miss it.
You don't work and play well with others anyway.
It's like the big angelfish in the tank that kills all the other ones.
Oh my God.
Well, he reminds me of walking rhetoric that I don't need to hear.
He's got some pretty compelling ideas.
Well, he has some good rhetoric. Some of them, like I said before, were good.
But then there's geometry.
I will say Nassim, he has figured out how to monetize what he's doing.
He has.
He's living the dream. Yeah.
Now we all need to mirror that and do that for ourselves, and we'll be good.
You got to do it with integrity. That's where I'll agree with you, Neil, on that. On the use of the rhetoric.
Well, I'm sitting here watching forms that are common to spheres, and then of course related to circles. And I think some of the problems is not thinking of them in 3 dimensions, thinking of them in 2 dimensions. It was a problem for our concepts, but still, you end up with some very special numbers. Just putting those together, play with a diameter of 1, and then watch the numbers start going from there. Once you realize what here's a radian, and so but I'm fascinated to find how this affects the little blue metal ball that we live on, and when you start seeing the fact that you have a sphere and it's a negatively charged and it happens to have 500,000 volts to an ionosphere around it, and it has a magnetic field as well, then to think that it doesn't have resonances and that these resonances don't affect the things that live on it seems rather short-sighted. So
yeah, it's
all open circuit.
Time is definitely part of the show, and then you have your different spatial, changes in amplitudes of anything. Once you have those fields, they're going to be changing in time.
Well, yeah, that's light,
right?
Well, light is the basic geometric form that creates everything else.
Okay.
Or pre-light. What's pre-light? Because that's like the field kind of that we're all talking about. Like
that's the time just before you had an idea. Get it? No, it's a joke.
Field like Gary was just talking about with field structure, Birkeland currents. Long distances of power lines of energy from one galaxy to another. There's a field geometry in there, and I've talked with Michael about it, and Terrence, and all of us specifically I get deep into the structure of these filaments. That there's geometry in the filaments, and technically it's plasma, but it's plasma in a few different types of modes. There's a few, and is that even light? I mean,
well, no, but
exactly.
There's if you really wanted to see how, if I was trying to envision it, like just to give you an idea, you have these charges, and just to say they're positive, negative, just like mass can be a certain mass. Well, one of the problems I have straight up when we talk about LIGO, the graviton detector or whatever the hell it is that nowhere in the formula for gravity or mass is time. Same with Coulomb's law. It's straight up. It's the force acting on any particle is equal to this K constant, then the sum of the two charges, brackets, over R squared. That's your basic R squared law. Change K to G and you end up with, gravitational law. But there's no time involved. It's straight up. Now, what is moving charges on a wire back and forth in an alternating current fashion is induction, which is basically causing a cyclical rotation, which is why you have these, things moving back and forth. Well, that's an pretty much instant force as well. It's just going back and forth, and there's no time. The length of the cycles are not changing. They're the same wavelength, 16.6.
What? I don't understand what you're talking about.
What I'm saying is that time is only affected with time variable things like light, but other forces are not related to this.
Well, you're going to say, okay, here's a Coulomb charge, and it's like, but you're assuming they're at a fixed distance in time, just statically.
Well,
So I think some thoughts that I have from what you were talking about, Neil, is I'm wondering if there's a place inside of a Birkeland current where it becomes timeless, because what I'm envisioning, what you're talking about, is of course you have the counter rotation of each one of these cylindrical shells, but then at the center, does it become timeless? Like at the center of an eye of a hurricane or a tornado, it's still, it's not timeless. But
what happens? Yeah, I was just thinking about that the other day. What happens to the pressure as you go? It's a low pressure in a hurricane, right? That's the center, right? Mm-hmm. What happens to the frequency of the material as you go in towards the center? Because it goes from like really high velocity material moving to like nothing.
Hurricanes being, I'll leave that alone for a sec, because the hurricane, it's pulling upwards, which is where it gets the lower pressure. Mm-hmm. It can even pull up water. That's why you get like the big weather. They come up. The hurricanes come on shore basically, and you have 50-meter swell or whatever. And
it rains fish.
And it rains fish. And crazy shit goes down. But a hurricane is like a very wide tornado, but it's still a charged sheath vortex, which is why when you take time-lapse photos, the eye of the storm is always alight with electricity. And it's trying to ground out between layers of charge in the atmosphere. And it's one of the situations that occur because of the fact that the water's so damn flat. That's one of the things that make it happen. It can't get rid of the charge naturally by going to the shoreline, so it builds up and tries to find a conduit to release this charge. What I think is interesting is a very common phenomenon that occurs in tornadoes, which is the weightless effect. I find that to be one of the most compelling, because if you understand that you have a positive inside charge and negative outside charge, then basically the ground feels like it's actually to the side, basically, and that's what things stick to a tornado, and then until eventually the tornado moves away and it gets flung to the side. But it's just a weird phenomenon that's obvious, but yet at the same time never talked about.
Wow. From someone who's experienced an earthquake out here, and I know this sounds like a left field shot, which often happens, but it's like the Northridge earthquake. I was in Sierra Madre, and it was significant. And I was awake at the time, and it's like the angle of gravity changed. I could feel it change.
So what are we looking at here? This is great. That's like what I was talking about. That looks like the point, the P1 and P4 looks like the point of the tetrahedron or the star tetrahedron.
Actually, I'm just going to finish up, buddy. The only reason I was talking about all that stuff was just basically to show how there are definitely waveforms in here, and figuring out what they are and how they relate to each other is something I want to hear more from people like you and people like Mike and Gary, because that's why I'm here listening to you, because, if it was all simple, we'd have it all figured out. So.
It is simple. It's just complicated.
It's just simple and complicated. I like that.
Mike has the simplicity. For sure.
Well, I'm looking at the diagrams, and I looked at the video yesterday, and I found it very difficult to find the elemental progression in the work. And that's why I left a message to take a look at how I divide up a sphere, because it seems to have a much simpler explanation and view. Now, I'm trying to understand what's being said here in the general solution, and I'm having a difficult time with it.
Yeah, I was just trying to kind of relate the conical radius. Like the conical radius is what would be the edge of a cone, and basically kind of relate that radius to the circles itself, and how they interact with each other, like kind of a flower of life pattern. Like how would those circles, dissipate and be equally distant and neutral to each other? And then there's only a couple harmonics that exist that actually do that. There's only, I could only find, a handful of harmonics that would just naturally resonate on the surface of the sphere.
Really?
And then, and they all correspond to, most conic solids.
See, I have a lot of these same shapes, but I have them in a much smaller configuration that forms all the way down to the core. This works on the surface.
Right. Yeah, exactly. It's kind of limited to the surface. By a large
right.
Yeah.
And
that's kind of what I was showing earlier, how it goes into the core with the Aurora star. That's showing you the core. And I know what Michael's saying, because this is topological, but it also goes out. I mean, because of the conics, it's not just a circle; it is a cone. And then you're saying, Michael, that you have some inner space geometry, or what they call mainstream science calls quantum geometry.
Yeah, I would say quantum. Did you have an image of that, buddy?
Of which one? Oh, yeah, he just had it. David, if you could please pull up that star, Aurora star.
Oh, yeah.
The image.
Yep.
The image I have of the Mickey ball.
Right there.
Well,
see that? Now, that's my division of a sphere.
Got it.
That's the harmonic division. Every single one of those is a equilateral triangle. And look, if you scroll up, David, that's the first one. This on the right hand side is what this is made of. So if you scroll, that's the first one.
We get the stuff out of the way here.
So you have the first one, you have the second one. You see that tiny little triangle on the right?
Mm-hmm.
Yep, that's equilateral triangle. Then you have all of them, and they all move. And I'm showing you the motion here through a sphere. If you could move through a wall, envision that line a wall.
You can if you go fast enough.
Yes.
You know it.
I think I experienced that one. Kidding.
So, Michael, if this could relate to some of your work or what you see here, because this literally is the division of a wave and the harmonic division of a wavelet. And I've applied it to many different things, but I'm curious to see some of you guys maybe what you think.
Well, that's why I was really anxious for you to take a look at the Mickey ball to see how it compares, because you could probably understand it better than I.
Okay. Can we pull up the Mickey ball real quick? Let me see that.
Yeah, let's see. Where's a good place to find it? Like, can I get it on from your site directly?
Where's the easiest place to find it?
I have it somewhere, but it's so dense.
We can find it
I
in
got
the
dense
video.
packing of images.
You can find it in video. I don't know if I have it. Just turn on any one of turn on geometry of light or any one of those.
Okay.
So faster. There we go.
Okay. That's the Bucky ball?
It goes into it, yeah.
Okay. Wow. Oh, okay. Yeah.
So from your tetrahedrons, that's a stack of 10 tetrahedrons. You put 20 of those stacks together, you get a sphere. Plus, in the process, you get every one of the other geometric forms, from octahedrons to dodecahedrons to icosahedrons to cubes. So I'm breaking down the sphere to its smallest part. And from your work, I was trying to find where the combination is, and I had a difficult time doing that.
Oh, from Gary's work?
No, from your work.
Okay.
This is always
from your sphere.
Okay.
Honestly,
it's always the challenges of like getting the cohesion of the ideas of the vision.
Okay. Well, how about I can show you. I can play a video here next. Or David, if you could. I think I already sent it to you.
what you actually reminded me of I can see the relationship between both sides of that form, how each one assigns itself to the radius of a circle. Actually, the first thing I thought of was Kepler. That's Keplerian orbits, and how you determine what an orbit's going to be. I thought it's not quite what you did, of course. I mean, obviously, he's talking about the area of triangles and how long it takes to traverse an area, but it's the same type of thing because you're looking at the area in a circle, which is a very similar equation. But
Buddy, I'm not sure what video you're referring to. So.
If you just Google the Doherty set, first video that comes up, please. I thought I sent it to you. I didn't.
chop chop. We don't have all day.
I'm trying, Massa.
Pish posh.
So it's great. This conversation is great because what we're all very interested in is describing the geometry of light, and the structure, the field structure, and so this is.
Is this it?
Yeah.
They'll likely be dancing.
Start. You just start from the beginning. If you just start from the beginning, it shows how it opens a little bit. So this is how currents move through space, according to the Doherty set and electromagnetic waves. I am an electromagnetic cartographer. I make maps So this would be coming off of the center. Then all of these waves, I think the Aurora star pops up right in the middle of the set too, so you can see how it fits into the wave harmonics and dyadics.
I totally relate to these images because they're inside of each one of my Trion Ray.
Mm-hmm. But you see how there's a progression inside of mine here?
Yeah, that when they keep progressing and progressing until they get all the way up to matter.
Yes.
Yeah. The scaling.
It's like fine silk.
Yes. If you look at most people's models, there's not a progression. Now, that means they're fake or false because everything's always progressing and moving and changing.
Well,
so
his is progressing linearly and you're progressing exponentially. It's just a different progression.
It is an exponential. This is the exponential field that we're looking at, and these are some of the geometries inside of the exponential field. You can actually see how it moves out in the what's that? The square, not the square root of 2, but the law of how light moves.
It's a cosmic pulse.
Yes, it is a cosmic pulse, and all the way from the micro to the macro, these Birkeland currents, this geometry, this actual structure is happening.
I agree.
And we all have a piece of the puzzle.
Where we get our vorticity.
Yep. Here's the opposing spiral vortices right here. There's 1, there's 2, and they're in phi harmonics. They're actually. So then you have the first or the second mode. Then you have the first mode, wraps it all together, shows you the structure right there. And there's one's larger than the other. And the ripping part inside of, or the collapse of the wave function happens right at phi inside of every wave. If you got the beginning point and the end point of every wave or wavelet, phi is exactly where the wave collapses. There's some of the, pause it right here, please. That right there, some of the fundamental structure of Aurora star that we were looking at. And I do two sets so you can see the progression, because phi is the solution to geometric and arrhythmic progression. So this is just
very Aztec.
That one is, yes, for sure, and reminds me of Minkowski space.
Mm-hmm.
So there you have it again, the Aurora stars without the details. If you were to put in more lines in there, leading all the way to the edges, or where the pine cones kiss noses, like Dan Winter says, then you would see the full Aurora star.
If you took everywhere that you have a straight line and made it a curved line, you'd get a more very interesting point of view.
I think that's what you're doing it here, right?
Yeah, it's very hyperbolic. I mean, the whole thing is, it's curvature. It is curvature. What is sound? Sound is curvature. What is the voice? What is our voice? What is vortexes? This is the vortexture of reality, if you will. A vortisphere. Look at Kaliman's work. Kaliman's work is all of his work. He talks about is vortex and sphere. Okay, Walter Russell is cube and sphere. But once you start getting deep into all of this stuff, you start finding that what precedes waves, what makes waves, is toroidal and helical forces. So what precedes the electromagnetic spectrum topologically and structurally is some sort of structure, some sort of toroidal helical field that comes out of this always emanating point sources that are inside of all atoms. I mean, think about it, dude. All of these atoms inside of us are radiating, but they're also they're imploding. Yeah, they're radiating and they're imploding. There's both.
Yep.
Within a sphere, what I've found, and if you look at the videos, there's at least 12 different toroidal happenings within the sphere.
Oh yeah, yeah.
So 12 is always that's the resonant point of spheres. 12 is just all over the place. And
the core of the sphere is an icosahedral form.
All right, which is right here, obviously. Right.
Well, down further. I don't know. Yeah, that's icosahedral. No, that's dodec.
It's both. It's both. They're duals of each other. So.
It's five.
But it's both of them.
Yeah.
Yeah. Let's see here.
And that's what creates the phase conjugate pump of life, because life is in phase conjugation, and it is invariant. It is scale invariant and logarithmic. So if you want to press play,
go ahead.
See, what I find, the way that you're describing it is something that varies over time, which, like I said, that's only the transverse waves. But there are other principles at work here more than just time varying over waveforms. There's the general structure of the platonic solids themselves. Always had a three-dimensional aspect to them, and I find it odd
right
that they're speaking from the past.
There's the wavelet with the toroids. Sorry to interrupt. It was on the screen.
No, that's totally fine. I see a relationship between these prion rays. That triangle form is the reverse of the torus, in a way, because that's the area. That's the if you were to try to draw the lines of force between 2 points, just as point charges, that's the shape you would have. So
that also happens to be a regular polyhedra.
Well, and it could form all the basis of all the other ones. So
it does form all the others.
Exactly. So there's definitely something very interesting with regards to seeing these relationships pop up throughout the universe, and I'm very, very interested to find out why that is. Some of them are this growth pattern and the scaling pattern. I mean, obviously, time scales the same as distance,
Yes.
and that seems to be true. But there are other forces, like I said, that are instant, and but that's only point charges or gravitational points or whatever. But nothing to do with. But there's other forces involved here other than just magnetism, and you have the voltage potentials between 2 points. They are mapped differently, and of course each wave across it, like a time varying wave across the ionosphere, making the Schumann cavity, or that type of thing. Those waves also count. So this is where you're trying to figure out the relationship of this, because clearly it's something that should be explored, and as many of you have attested to, sorely lacking in explanation. And I don't mean I just mean in conventional sense.
I think we're trying to describe everything in reality using one force, and I think that's what we're always doing. And then we start to find that there's this force, and we call this that, then we call this a different name, and that's gravity, and this is. But once you start to understand that everything is one, which is what we've been trying to do, the grand unified theory, the gut, then you start to change your monoptic to multi-optic, or maybe it goes way back and goes right back to being monooptic again, and then that's monotheism, and then monogamy also.
From the one comes the many.
Mm-hmm.
That is the basis of it. Every religion is based on that theory of the one, the star seed.
Right. The eternal stillness.
They're actually...
it makes so much more sense when it's one, then we can make sense with it. Because a double-minded man is unstable in all of his ways, so you're thinking of reality like this, wait. I just got to try to make it make sense with one fundamental force. Then you see that charge rotating charge is gravity, and things like that. And then all of a sudden you start, for example, that's an example. You could see all of the charges and everything in reality being one.
I can see the argument that technically when I push down on a table, it's not anything no particles are actually touching, even though the easiest way to do the math is to use particles. But if I was to explain it differently, I could say there are so many electron volts pushing against, the charges are building up here and pushing against that other object, and that's what's actually preventing me from, and it's resisting this throughout its entire structure to, hold itself in the same shape, and then these forces are acting. Now, there's argument, just like Edwin would say, that there is to get rid of the weak force, I can see. But you've described two forces on your first go, and I think that there's at least four, and if you think about it as sort of EMF and MMF, but there's also a torque to the MMF. And the MMF is not really a force as it is a excuse me.
What's MMF?
Basically a magnetic field. Yeah, and it's not really. In fact, it's a misnomer to have motive in there, because trust me, there is an electric force, and it will cause a force. But it is a curl, yeah, and it involves alignments. So this is, and of course, the weak force of gravity, whatever spawns that. But I mean, getting down to that much. But those, when you get right down to it, are basically just Maxwell's equations with gravity tacked on. And this is why I'm so fascinated to see how this could, start seeing where the golden mean pops into these, like on if you assume a diameter of 1 and you start doing divisions, and then you're starting to see resonance patterns and so forth. And it's very deep. And it's not. It's very exciting, and and of course it begs the question: what were the ancients talking about? Why the fascination with 12, 3, 6, 9?
Right. And they pop out of it.
Yeah.
Just I mean, without like PhD level mathematics, they just pop right out of it.
Well, it all nests inside 12, and then it's centered by 13. It's really 13, but the center, it goes uncounted.
Correct. That's true. Can anyone give me some feedback on what a particle physics is?
Where it came from? It's like you ever see the game Mousetrap? It's like a really super complicated to catch a mouse. It's like where you could have captured it really quickly. That's where it came from. Like a Rube Goldberg machine.
A big friggin' waste of money is what it is, in my opinion.
What I found looking it up is that physics came to the point where they decided that light is so small and so fast that we'd never be able to see what it looks like, because it's way too small for anything that we have to observe it, and it's way too fast. So we'll call it a particle. Now, that's
how they turned everything upside down. They turned the tool into the thing that they deified versus the thing itself that they were trying to measure. Yeah.
Who's they? No, I'm just kidding.
Yeah, we know.
Big science.
Those days over
there. There is some truth to that, but it's mostly, in my opinion, it's matter. I mean, some people have conspiracy theories, and there are some points to be warranted. But generally speaking, most of what people are talking about is something to do with not having the vision to recognize the situation and
look
not
at
being
the
willing to
term.
change.
Look at the term quantum. It's to count, and it's this desire to be able to say, I can measure this, therefore I'm the king.
I'm smart.
And it's like this is absolutely like just it's often referred to as just the lowest type of analysis. You're not looking at the fundamental.
Actually, it's worse than that.
Something.
It's not science.
It's not. It's accounting.
Well, what I meant, let me be frank, there's scientific aspects, but what I meant was, and just like astronomy or cosmology, once you leave the realm and go into theory, and that you can never build it on Earth, you can never compare with experiment, therefore you're talking shit. And one of the things that happened to pop in when you're talking about stuff like that is when they should have realized, just like Schrodinger was saying, like, and people like Tesla were going, you're out of your friggin' minds, guys. You got to keep this stuff real. You're going off into la la land of reification and pseudo pedagogical concepts, and they're losing what, you can talk about having 12 layers of reality or whatever, but in the end of the day, you live in a 3-dimensional friggin' world, and time moves this way. That's what you got,
But there are 12. Just to get back to the kind of this interesting 12 aspect, and particularly our 12 hours a day, 12 inches, 12 notes on the keyboard, which is a big one, by the way. And why are there 88 constellations and 88 keys on a keyboard? That's pretty interesting to me.
That's actually something I never thought about.
Is that crazy? Yeah. But
what about 7 oceans and 7 continents?
Why are these so fundamental in our reality? And they're just basic. I mean, you can get a 4-year-old.
I can answer the 7 thing, and
7 layers of skin too.
Well, what I mean is that exploring the Velikovskian aspects, you're going to end up starting to talk about petroglyphs and what you saw in the sky, and et cetera, et cetera. And of course, since we're dealing with electromagnetism, patterns will invariably become part of the culture. And part of the things I wonder is, it's as much as I've seen the beauty that is drawn into these things, that shape that all 3 of you talk about, being the flower of life symbol, is now I got to think about knowledge that without a computer. Like, I got to do this in my head. Okay, and without having needed to even do complex math, I can do it all either on my fingers or just in my head. Now, I would like to think that I'm a fairly smart fella, but I don't play with pi in my head. I'll play with radians in my head, and I will start dealing with things on a way that my brain can process it. This is something I find to be fundamental. Now, trying to describe something 3-dimensional. Yeah. You don't play with that. It's an asinine long number, and you don't play with that.
Right.
All I meant. It's irrational, so you don't play with it.
Yeah. So as B is.
But there's more to it when you start getting into these patterns, and they're sitting there, and then I think back to Plato, and then the idea of, well, these can be represented with electromagnetism and charges. Could there be enough charge in the atmosphere to, with incense, be able to sort of create forms, because each of these relate to a sound as well, and it's stuff like that makes me question what these ancients were talking about. I mean, fundamentally, and obviously trying to hide, because knowledge was being
it's interesting, that direction. It's like Flatland. I don't know if you're familiar with that book. It's kind of, but where it's kind of a classic, right? But we actually kind of live on a flatland with Euclidean. This is where Mike is really bringing this to the fore, and as Gary. But it's like this, everything's curved, and Terrence, by the way, of course, right? But it's
and
like
Walter Russell.
And Walter Russell and all these characters, all these new voices that are kind of popping out of the woodwork here. But we live,
except for the long dead one, yeah.
Yeah, right. But we live in a Euclidean. Our mathematics is based all Euclidean, and you start bending that Euclidean into either concavity or or what's the other one? Convexity. But the one's hyperbolic and one's elliptical, and you start, and all this stuff starts popping out of it, and it's like and all of a sudden you jump out of flatland.
If you look at this and you see the secret is you're looking at a two-dimensional representation of a three-dimensional form.
Right.
Yes.
And that third-dimensional form is the secret that's hidden in plain view.
In plain view, right.
And the three-dimensional form is actually
a
shadow of a four-dimensional, higher dimensional projection.
No, it's not a shadow. No, sir. It is a solid form.
I know, but it's being fed by currents outside. All three-dimensional matter is being fed by currents outside.
Right. Oh, absolutely.
From a fourth dimensional, higher dimensional hot vibration, which is it's being fed inside and outside.
Well, since it is a form that's solid and it spins and it contracts
it's not solid. It's not solid. Nothing's touching. So you got to remember that it's mostly space. So
space is. I believe that space is created by a solid. Space goes in all directions. It's a solid thing. You can move through it. The same thing with each one of those little cusps. Instead of being a two-dimensional, they're a three-dimensional. And if they're three-dimensional, they're a vessel. And if they're a vessel, they can hold something. And if they can hold something, they can hold a thought. And that original thought is pattern recognition. And it keeps connecting and connecting and connecting and keeps going in many directions until it becomes self-aware. And that's us.